This is a 2011 16th question. They are asking the center of gravity of a solid hemisphere, right? A solid hemisphere of radius what? Radius A. Radius A. So to do this, what should we do? I'm not going to do this because like we have already done these things in theory. You need to draw the place the hemisphere. Take the 2D of the hemisphere. So this is a solid hemisphere, and place it on y and x axis symmetrically, which means y is equal to 0. You need to show from the base of the hemisphere that the center of gravity exists at a distance. At a distance, you need to show this xy is equal to what? Xy is equal to 3a over 8. You need to show this, right? Xy is equal to 3a over 8. For this, of course, what you need to do is you need to use integration, right? So, like you need to first of all consider infinitesimal element, right? So, yes, this will be the infinitesimal element, and this will be similar to what? This will be similar to a disk, right? This will be similar to a disk. Yes, this will be similar to a disk, right? And so this will be x. This will be what? The radius A. What will be the radius A of the hemisphere. So radius of the infinitesimal particle is r. So r can be written as a squared minus x squared root a squared minus x squared root. So okay, and then like so this is a cylinder. You need the, since this is a solid infinitesimal element, volume is equal to what? Pi r squared h. So h is going to be dx. You need to select a very small particle of length dx, and pi r squared h. So h is done, r is already got. So and then so this is volume. So therefore, like you can write dm. Dm is equal to rho dv, right? So rho pi r squared h. So like you can and put it into the definition. X bar is equal to x dm over dm, right? And then you can simplify. You can integrate from where to where. So from 0 to a, right? From 0 to a, you can add this. When you add them, you are going to get the complete hemisphere, right? So yeah, that is it. I'm not going to do that because we have taken a lot of time and discussed them in detail, right? So you will have to go through that. So here, of course, you will be getting for this part maybe around more than 20 to 30 marks. Definitely, maybe around 25. It's confirmed, right? So 30 marks to 25 marks is sure. Like you can, if you by heart these, like you know, you do not have to by heart these things, but still, I don't know. You can take these marks from home itself, right? So like learn to integrate and all the 5 or 6 to 7 objects we did, right? So yes, I think that's fine. So you can show that this xy is equal to 3a over 8. That will not be the. Sorry, just give me a second, right? Yes, it was my alarm. Right. Okay. So fine. You can prove that. It's not going to be a big issue. Let's do the question, the below part. Right? What do they say? The inner and outer radii, of a uniform solid hemispherical shell are A and B. It's like this. there is a uniform hemispherical shell. Uniform hemispherical shell. Think it in 3D. So coconut shell, it's a shell, right? So it has a thickness. So we are saying simple A is the inner diameter while simple B is the outer diameter. Simple B is the outer diameter, right? So think about this in 3D manner. I have taken only the cross section, right? And they are saying show that the distance of center of mass from the center along x-axis of symmetry is this. Yes, that will be the question. Right. So first of all, we need to represent this on x and y axis. On x and y axis such that this remains in symmetry. Right. So yes, let's draw that. Right. Right. Okay. So this distance is what? Simple A. Outer diameter distance is simple B. Right. Okay. So this is what actually like I would integrate. You do not have to integrate here, right? You can use the combined object theory, finding center of gravity of a combined object. So yes, it's true. There's no combined object here from a hemisphere. You can make this a combined object. Also, from a hemisphere, you cut out another hemisphere. Right? From a solid hemisphere. So from a solid hemisphere of radius capital B, from a solid hemisphere of radius capital B, you are going to cut out another hemisphere of radius simple length. Another hemisphere of radius simple length. Right. So let's go for the table. Object. Mass. And then distance to center of gravity from origin. From origin. Fine. So first of all, let's take the larger hemisphere. Hemisphere of radius B. So mass, how is the mass written? Mass is written density into volume. Density, let's assume rho. What is the volume? Volume of hemisphere 2/3 phi r. R radius is what? B. 2/3 phi r cube. So therefore, this is the volume 2/3 phi b cube. What is the distance to the center of gravity of this? from origin. Somewhere here maybe. So what was the distance to what was the distance to the center of gravity of a hemisphere? We proved that above. 3a over 8. So here the radius is b, which means the radius is going to be 3b over 8. 3b over 8. over 8. And next, let's go for the smaller hemisphere, which is cut out. Hemisphere part which was cut out. Simple A. Rho. Once again, rho into volume. Volume is what? 2/3 pi A cube. So where is center of gravity of the smaller hemisphere? From the center, it's 3a over 8. So now the shell. So from this, you need to subtract this. From this mass is subtracted. So 2/3 pi b cube minus rho 2/3 pi a cube. So what is common? Rho 2/3 pi. Rho 2/3 pi b cube minus a. B cube minus a cube. B cube minus a cube. Right. So where is the center of gravity? Center of gravity is at x bar. I don't know, somewhere here maybe. X bar. It's easy now, right? So we do not have to do anything else. Straight away, how are we going to put this into the equation? So this product, okay, so this is what how from this, if you subtract this, you are going to get this. Which means from this product, if you subtract this product, you are going to get this product. Simple, right? So from this, if you subtract this, you are going to get this. Which means from this product, you need to subtract this product, you are going to get this product. Right? Okay, let's apply this product. Yeah. Rho 2/3 pi b cube 3b over 8 minus this product, right? Minus rho 2/3 pi a cube into 3a over 8. So it's going to give you what? So it will give you this product. 2/3 pi b cube minus a cube x bar. So here what are common? 2035 common. So another row is there here, right? Okay, row is there common. Along with row, it cancels. Cancels along with row. right? So okay, let's see what's remaining, right? B cube into B is B to the power 4. It's just simplification. 3 over 8 B to the power 4. 3 over 8 B to the power 4 minus 3 over 8 A to the power 4 is equal to B cube minus A cube. X bar. X bar. So X bar is what? X bar is equal to, take 3 over 8 common out. What is it? B to the power 4, A to the power 4. B cube minus A cube. Yes. Okay. Right. So how can you expand this? So now it's simplification, right? So I'm going to expand this. B squared to the power 2 minus A squared to the power 2. I'm going to expand this what? B minus A squared plus B squared minus AB. Sorry, plus AB. We need to know the expansion of B cube minus A cube, right? B cube minus A cube, the expansion is B minus A, B minus A, B minus A squared plus B squared plus AB. It's not 2AB, it's AB. This expansion is expected to be known, right? So I think you are okay with that, so therefore I will move on. Right. Further, 3 over 8 B squared. So what is this? Difference of two squared. Difference of two squares. B squared plus A squared. B squared minus A squared. B minus A squared plus B squared plus AB. X bar is equal to 3 over 8 B squared plus A squared. Once again, difference of two squared. B minus A, B plus C. B minus A, so you can cancel this to this, which means what you are going to get is X bar is equal to A plus X bar is equal to 3 over 8 A plus B, A squared plus B squared, A squared plus B squared plus AB. Was this the answer? Yes, right. This is what they have asked to show us. So we have obtained the center of gravity from the center to this shell. The center of gravity of this shell is obtained now. From where? From the center of the shell, right? Okay, now let's see what happens. The hemispherical shell rests in equilibrium so that its curved surface is in contact. The hemispherical shell rests in equilibrium, so it's in equilibrium, right? So okay, it's in equilibrium so that its curved surface is in contact with rough horizontal ground. Rough. Okay, so the ground is rough. Rough horizontal ground and equally rough vertical wall. Right? So it's like this. There are two walls. kind of two walls. So this a vertical wall and a rough flow, rough wall, rough flow. So the shell remains in equilibrium. How actually? By being in contact. So the curved surface is in contact with both this and this. So how can you draw such a thing? It's going to be difficult somewhat to draw. All right, so it's going to be like this, something like this, right? So it's touching both the balls in equilibrium. In equilibrium. All right. Okay. So we need to yes, they are saying it's in equilibrium. So before we proceed with what they ask, let's mark all the possible forces. Let us mark all the possible forces, right? So okay, if this is the center, reaction will definitely go through the center. R, reaction will go through the center, right? And then this reaction also goes through the center. S, because like, if there are contact surfaces, I have told you always there's going to be a reaction. If there's contact surfaces, there's reaction. One contact surface, reaction. But and also I have mentioned you, when there is a curved contact surface, the reaction goes through the center of the curvature. So what is the center of this curvature? What is the center of this curvature? Both goes to the center. So where is the weight going to act? So this is the center. From where? From here, X bar, somewhere here. Somewhere here, X bar. What is this? W, the weight, total weight. What is the total weight? This. I'll mark W, right? So then, and I'll not write this for the timing. What else? Are these the only forces? Can this be in equilibrium like this? Upward, downward, to balance this force, there's no other force. It can't be in equilibrium. They have given both the walls, the vertical wall as well as horizontal wall, vertical wall or as well as horizontal flow, both are equally rough. Both are equally rough. Equally rough. Right? Equally rough. So, how to mark the directions of friction? If there's rough, if it is rough, there should be friction. So now, like obviously, in applied, there's a lesson called friction also. It's like even the friction lesson is going to be somewhat complex. Right? So complex as equilibrium. Right? So like here, of course, there's no much friction involved, but still you need to know to mark the direction of the friction. This is how you mark the direction of the friction. So first of all, you assume there's no friction. Friction nagilaitandu. Friction natham. Where the slip pen? මෙන්න මේ විදිහ. අර පැත්තට ස්ලිප් වෙන්නේ. මෙයා පල්ලෙහාට යනවා. අර පැත්තට. නේ? එතකොට if there is no friction, so this part comes down, this goes that side, which means by friction only those two motions are prevented. So මෙහා පැත්තට යන එක වළක්ව ගන්න නම් friction එක තියෙනෝනේ මේ පැත්තට. friction එක තියෙනෝනේ මේ පැත්තටද? මේ පැත්තට. equal frictions කියලා කියනවානේ මොකක්ද? equally rough keyword. It's not going to be the same friction. Right? Equally rough means the same coefficient of friction. Mu සමානයි. mu සමාන. right? and මෙයාට ඉන්නේ පල්ලෙහාට. ඒකට friction එක එයා balance කරන්න right. So 1, 2, 3, 4, 5. 5 forces are there. 5 forces are there. 5 forces are there. Okay. So the thing is, right? Now we need to, now let's see what they are asking, right? So now what you need to understand is not the simplification and all. As always I mentioned, see how I step by step approach the question, right? So yes, I marked all the possible forces first. I did not even look at what they are going to ask. So I know definitely if it's an equilibrium question, we will have to deal with forces and all. So therefore all the forces should be marked. Therefore I marked it on the diagram first of all, right? So they are saying show that if the equilibrium is limiting, okay, if it is in limiting equilibrium, the inclination of the base to the horizontal is the inclination එක ගහන්නේ. මේකනේ base එක. the base එක inclination එක horizontal එකට දක්වන angle. This is what they are asking. They are asking show that if this is in limiting equilibrium කියන්නේ that listen on the menu. It's in its maximum friction. Then this base of the shell is theta inclined to the horizontal. මේ theta කියන එකේ අගේ නෝක කියලා පෙන්නන්න ඕනේ. So it's going to be a very complex answer solution. That's why it will take a lot of simplification, right? Not actually, right? So you can easily get that answer. So although it seems to be very difficult, it's just a small question, right? So it's yes, you can see this. This is how it's going to be done. Yes, I will use the space. Okay. All right. Fine. So now to do this, you need to know equilibrium somewhat, right? So to apply equilibrium and all. Fine. Around the center, I'm putting a moment. I'm applying a moment. Around the center, I'm going to apply a moment. around the center, I'm going to apply a moment. S. Yeah, no need of applying moments. It's going to be complex. I'll apply. Okay, so equilibrium questions. What do we do usually? We consider upward equilibrium, horizontal equilibrium, upward equilibrium, horizontal equilibrium. As usual, let's do that. So yes, upward equilibrium. Upward equilibrium. That means what? R is equal to R plus F2 is equal to R plus F2 is equal to W. What is F2? F2 is so mu. They have given the coefficient of friction mu. Both similar coefficient of friction, equal roughness. They have mentioned. F2 is mu S. Mu R ne saman mu into S ne. Mu into reaction. Right? So it will be mu into reaction. Mu into reaction. Right? Not R. Mu into S. Mu into S. Right? It's equal to W. First equation. Right? Mu into S equals W. Another equation let's take by apply equilibrium. The horizontal direction. S is equal to what? F1. S is equal to F1. Harder the equilibrium apply करें मैं shell लेकर आए shell लेकर equilibrium apply करें. S is equal to F1. F1 is what? F1 is mu into R. Mu into R. And so if this is theta, this is 90 minus theta, this is theta. If this is theta, this is 90 minus theta, this is theta. Right? So what is this? This is X bar. So this length is what? X bar. X bar. Right? X bar. Yes. This is X bar. I guess it's more clear somewhat. Yes. Right. So that is X bar. So now we are going to take what? We are going to take moment around this center point. This is O. I will take moment around this center point. Moment. When you take moment, R or S will not come into the equation because it goes through the point where I take the moment. R or S will not come into the equation. right? So yes, let's take W. So W into x sine theta, x bar sine theta, x bar W into what is the perpendicular distance to W? X bar sine theta, x bar sine theta, x bar sine theta, right? So this is the only clockwise moment, from the friction, anti-clockwise moment, right? F1 into what is the distance? B. This distance is B. F2 into once again B. F2 into B. Right? F2 into B. It's clear, right? Yes. F2 into B. So now I'm going to do certain things, right? Let's take B out. Let's take B out. B out, which means F1 plus F2. I'm going to take B out. B common, right? I will take it out. So yes, F1 is what? Mu S. Mu S. This is mu R. Mu S plus mu R. All right. So you can take mu out. You can take mu also out. S plus R. So S plus R is what? Uh, what you can do here? S plus R is there. We have another two equations. Somehow we need to eliminate this S and R. S and R. So yes, I will have to find S and R now somehow. So two unknown equations. I will have to find S and R. So shall I use the below space? I will use the space on that side, right? Right. So sorry about the space issue because it's very difficult to manage the space, right? So I'll use the space here to find S and R by using the first two equations. So here S and R, the S reaction and R reaction is there. I need to eliminate this S and R. I have two equations already. So by using those two equations, I will find S and R, right? So yes, you can find instead of S, what can you write? So from the first equation, right? From the first equation, what is the first equation? R plus mu. S, instead of S, what can you write? Once again, mu R. mu r, right? Mu r is equal to w. So r, when you take out 1 plus mu squared is equal to w. R is equal to w over 1 plus mu squared. 1 plus mu squared. So S is what? Therefore, S is mu. What is R? So R, W 1 plus mu square. So S is mu W 1 plus mu square. Mu W 1 plus mu square. So S and R is kind of okay, right? I'll use the space below, right? So S and R, okay, I'll subject sine theta. Sine theta, it is equal to mu b over w x bar, right? W x bar. S and R. S is what? S is mu w 1 plus mu square plus R is what? W 1 plus mu square, right? So this W to W cancels, right? So 1 plus mu squared, 1 plus mu squared is what? It's the LCM. So mu b mu plus 1 plus mu squared into x bar. So this is not our answer, right? This is not our answer. So what is our answer? We need to substitute x bar also. Then only we will be getting our answer, right? So theta is equal to sine inverse. I'll send sine inverse to that side. Sine inverse this mu b mu plus 1 plus mu squared. X bar is what? 3 a plus b, a squared plus b squared, and 8. This thing goes up. 8 a squared plus b squared plus a. This is the answer. This is the answer that they have been given. They have given. So it's a small simplification. So I guess you understood up to this point. So like consider this, right? So reaction goes through the center. Reaction goes through the center, and also friction. So I mentioned you how to decide the direction of the friction. So if you leave this, this will rotate in, like this will slip in this direction, which means the frictions are balancing that motion, right? So yes, okay. So these are the forces. Straight away, first of all, apply E. So this is in equilibrium. They have mentioned that, right? So therefore, it's in equilibrium. So it's in vertical equilibrium also. So let's apply vertical equilibrium, which means upward forces R and F2 should be equal to W. Should be equal to W, right? So F2 is what? F2 is mu into S. Mu S is equal to W. And I applied horizontal equilibrium, right? So that means S is equal to F1. S is equal to F1. F1 is equal to mu into R. Right? Okay, that is done. And then next I applied what? I applied a moment. A moment around whom actually? A moment around O. Why did I choose O? So obviously you know to include theta. So the මේවට apply කරා කියලා theta වෙන්නේ. Theta නේ අහන්නේ. Theta ව set කරගන්න ඕන නම් අනිවාර්යෙන්ම අපි moment එකක් දාන්න වෙනවා. Right? So that is why I applied a moment. So equilibrium ධම්මර theta ආවේ නැහැනේ කොහෙන්වත්. So to relate theta, if I could apply moment around a certain point, I'd be able to get an answer, right? So therefore I chose O. Why O? Because O හරහා තමයි forces දෙකක් යන්නේ. එතකොට ඒ forces දෙකම අපිට O වට දැම්මම neglect කරන්න පුළුවන් moment එක ගන්න ඕනේ. right? Because I ඒ O එක හරහානේ යන්නේ forces දෙකම. ඒකට අපි දන්නවා. මොකක් හරි moment එකක් දාන point එකක් හරහා force එකක් යනවා නම් එයාටයි ඒ point එකට perpendicular distance එකක් නැහැ. එතකොට moment එක දාන්න බෑ. බිඳුව. Right? So therefore I applied moment. Now W perpendicular distance x bar sin theta. F1. So make a perpendicular distance. B. We make a perpendicular. F1 B. A better moment. Moment plus F2 B. Let's say F1 B both F1 plus F2. F1 can mu S, F2 can mu R. Mu both S plus R. ඊට පස්සේ මේ equations දෙකෙන් SU R සුළු කරලා ගත්තා. SU R. ඊට පස්සේ ඒ SU R ගත්ත එක මෙතනට දැම්මා. මේ වගේ එකක් ගත්තා. ඊට පස්සේ x bar වලට මේ ගිහිල්ලා substitute කරා. ඔච්චර. සුළුවත් කරේන උත්තරේ විදිහම තිබ්බා. That is the answer.